In this lecture, we're going to talk about the Biot-Savart law. That law is mainly used in physics and is also applied to aerodynamics. To understand this, consider this arbitrary body, a fluid body, and think that whatever happens here, we want to evaluate what happens in this location. So this vector is going to produce a vector velocity here in the z direction going downwards. Okay, so to understand this, you have to use the right-hand rule, right? So if your vector goes, if this is going in this direction, right, you can see that this is going in this direction. In other words, it's creating a flow in this direction right here, dl. Okay, that's how we know this is going in this direction. And from this point, it's always pointed towards the point where your point is interested. And this point, again, this point VP is 90 degrees, is downwards. Okay, it's not in the same plane. It's in the other plane. It's like in this plane right here. So this is always pointed in this direction. And you can see that that's producing a circulation that produces, if you use the right-hand rule, produces a vector downwards. Okay? So if we do the derivation, we know that the vector is actually, your velocity vector is given by the following equation. And your dl times dr. So dl times dr is equal to minus r sine theta dl times ep. EP being the direction in this direction right here. H is equal to, the value of H is r sine of theta, if you would. And then L is equal to r cosine of theta. Okay. So if you keep moving on here, then you keep replacing all these values in here, each one of these values. Then you can simplify this and replace what dl is. You come to this equation. And this equation, when plugged inside here, then you find this gives you minus cosine of theta and of angle 2 and angle 1. And this is your final expression that we really care for. And this is basically comes from this figure. So this is theta 2 and this is theta 1. So your velocity then is equal to this if you're working actually infinite segment, 0 to infinite. But I'm going to do minus infinite to infinite, but we'll talk about this in a minute. Then here, if you had a case like this where both of these angles are identical, in such a case, and you replace everything, you can show that this simplifies to this nice expression right here. Okay, it's kind of nice because you use this a lot. And if we said 90 degrees, your angle is on this side, then it simplifies to this nice expression. If you're working with this expression right here, you're working on this one, then this simplifies to this expression here. Okay, so these are kind of nice simplicity, simple values to use. Just want to point out a few things. Just remember that your theta 1 is here, and we only care for alpha, okay? So 100 minus theta will give you the angle that you're looking for. So if you're working in a circular section now, the analysis is still a little bit more straightforward. Again, this goes towards the point, this goes in this direction. So this is this will give you a negative. This is the rotation. This is gamma, that's the rotation. And that will give you r squared, the theta, EP, r squared, all this cancels out. So at the end of the day, you end up with this. Note that I'm going 0 to pi, 2 pi, because it's the whole circle. But if I was only half the circle, then it was 0 to pi. Okay? Just keep that in your mind. There is a nice comparison for the infinite. So it goes from minus infinite to infinite. This gives you, there's a 2. And when it's semi-infinite, starts 1 point and goes to infinite, then that has a 4. Okay? So all this is actually connected to vortex vortex filaments that we talked about before. Remember, we derived this equation. And when you have the Helmholtz equation, the case for straight filament, we show that this is equal to this. And then for minus infinite to infinite, it comes from this equation right here. Okay? Now, Helmholtz theorem also says that the strength of the vortex filament will be constant. So that means if you have a gamma here, that gamma will be the same across everywhere across that line. Okay? So that circulation will be the same. The vortex filament cannot end in the fluid. It must extend to the boundaries of the fluid, so which can be minus infinite to infinite or form a closed path. Okay, so this is how we use all three, basically give you the same answer. So what we're going to do next, we are going to apply these to two separate examples that will help you to grasp these topics.